So now to the final part of the lecture. I hope you are still with me, less bored than last lecture at least. We talked that we are going to mostly cover monolithic kernels in this course, and this is the most widely used operating system, or at least it is believed to be the most widely used operating system. And I'm going to just say why I just said believed. It's basically Linux, Windows, Unix, BSD, Mac OS X, and Android, you name it. All of these are called monolithic kernels. They're built with lots of functionality inside the operating system. Everything that you can fit in the operating system, you just throw it in. And it has two central ideas. It provides the hardware abstraction layer, and it has dynamically loaded device drivers. We talked about the device drivers now a couple of times, including just a couple of slides ago when we said that since you have the open close read write interface for your IO, you need dynamically loaded device driver. You need the device drivers to actually know how to handle this. Hardware abstraction layer, HALs, are portable interfaces to machine-specific operations. So you basically have a HAL, hardware abstraction layer, for my Mac, which is completely different from my Lenovo, which is completely different from my desktop, which is completely different from my server. They have different capabilities, they have different hardware. So you want hardware abstraction layer on all of these machines, although they might have completely different, wildly different processors. Like this is Intel, this is AMD, this is even ARM. So if you're running on for example, a Raspberry Pi, Linux on a Raspberry Pi, because it does run on a Raspberry Pi, now you have different hardware, very different architectures, but you have the same Linux. So this is the hardware abstraction layer at work. You do not really realize that while the operating system is much different because of this. And when you're basically trying to build an operating system to work for different hardware, for example, between AMD, Intel, different Intel family architectures, and so on, you just change the how. You do not go and change the upper layers of the operating system. You do not rewrite the whole operating system. You just rewrite the hardware abstraction layer. Then you have dynamically installed device drivers. So if I'm adding new devices, I should be able to basically load it easily, and the operating system should be able to get this device driver to run seamlessly. So if I add new headset, new keyboard, external hard disk, I mean, the operating system it should not give me issues. When this first came out, they called it plug and play, and it was famously known as plug and pray because it didn't really work. You would need to actually restart your computer to get your speakers to run. Not anymore, thankfully, but this is basically essential. So this is very nice, but it resulted in bloating in the number of lines of code in an operating system. So what you're seeing here is actually the number of lines of code in the Linux operating system. And you can see that it is over actually 25 million lines of code. It's a huge beast. It's really a very large beast. And it's just increasing, and it's never decreasing. It's just increasing. People say that Windows has at least 50 million lines of code, so double the number of lines of code of Linux. Because, well, you get right now when you basically get Windows, you get all these fancy GUI things like the interface for Windows, the Windows Manager, and all of these things. And these all now are becoming more and more part of the operating system. Linux has similar GUIs now and so on. And the fact is that you have 50 million lines of code or 25 million lines of code, you have 25 million potential security risks in the most central part of your operating system. So this has been debated among operating systems researchers if this is even the way to go. Many people think that no, operating systems are now bloated. We should go to microkernels. Microkernels basically is the opposite of what you see with monolithic kernels. You basically say that the operating system is just the things that you need, meaning it's the scheduler, it's the files, it's the very basic functionalities for processes, but everything else that is not really needed to run the CPU is not part of the operating system. And then they run at more like user level servers. They run more like applications rather than an operating system. This includes all the drivers, all the network stack, all the file system, and use the syscalls instead. The most famous example of these systems is Minix. Minix 3 now is, I think it's Minix 3 if I'm not mistaken. And Minix has been advocated by a very well-known researcher in the field, Andrew Tannenbaum. He's actually one of the forefathers of the operating systems field, and Minix was, as I said, has some of the concepts of Minix found their way in Linux's early days. The way I said that it's believed that monolithic kernels are the most used kernels on Earth was that very recently it was discovered that Intel has been installing Minix, the full operating system, on all of its chips. And since it's very lightweight, most people did not really realize it until very lately. So now almost all Intel all Intel chips that have been in production for the past few years have had Minix installed, like fully fledged operating system. And this is security risk, of course, because it's an operating system that you cannot really that runs and controls the processor, and you have no control over it. Tannenbaum has actually some very nice and nasty blog where he basically talks about why monolithic kernels are bad, why we should refrain from using them, and why we should be using microkernels. I think this is basically my last slide. I would highly suggest that you go and check Andrew Tannenbaum's blog because it's really informative. It's quite nice. And oops, am I going the wrong direction? Yes, I'm sorry. It's 2 a.m. here and I'm pretty sleepy now. So next time we will be covering chapter 6, and that will be hopefully more fun things than even today. Thank you, and I will see you on Thursday. So very fast, Thursday we meet. Everyone, please try to come because otherwise, well, yeah, things get a bit complicated, and then we talk about when you need to come and when you do not need to come. Thank you.